Welcome back to week 10 of the ma161 calculus. My name is Götz Pfeiffer and this video is about critical points. Critical points are those points on the x-axis where a maximum global or local or minimum of a function could possibly occur. We develop this notion here in order to then formulate a strategy that helps us to locate precisely the positions of the local and global extrema. We start with a theoretical insight, a theorem called Fermat's theorem. This is the same Fermat as of Fermat's last theorem fame, but this is a different theorem. And it says that the tangent at a local extremum, if it exists, is horizontal. Or in terms of the derivative, Fermat's theorem says if f of x has a local maximum or a local minimum at the point C, and if the derivative f prime of C exists, then the derivative f prime of C is 0. For example, here's the typical graph of a quadratic function. The function defined as f of x is x squared plus 2x minus 8, and this function obviously has a local minimum at -1, judging from the graph. If you want more evidence, then you can calculate values nearby, for example, and the value at -1 itself is -9, as you can easily see, and nearby, say at -1.1 or -0.9, the value turns out to be a bit bigger, -8.99. So in that sense, the value at -1 is bigger than the values nearby. That's not yet the level of precision that we really like, but we're getting there. So here we just want to verify the statement of the theorem. So we check the derivative, which of course is 2x plus 2. Evaluating the derivative at -1 gives -2 plus 2 is 0, just like the theorem predicts. And the tangent at this local extremum, at this local minimum, is parallel to the x-axis. It has slope 0. It's important to get the logic of this theorem right. So let's read it again. It says if f has a local maximum or minimum, and if the derivative at C exists, then the derivative is 0. That's an if-then statement. It's a logical conclusion which doesn't work the other way around. More precisely, it would be wrong to say that f of C cannot be a local extremum just because the derivative doesn't exist at C. And to illustrate this point, here's the graph of the absolute value function. It has obviously a local minimum at 0. The absolute value of 0 is 0, smaller than any absolute value nearby. But the derivative doesn't exist. It's a situation where the derivative doesn't exist, but still the function has a local minimum. The other way one could get the theorem wrong is one cannot conclude that f of c is a local extremum just because the derivative is 0. What the theorem says is logically the the converse. If it has an extremum, then the derivative is 0. The standard example to illustrate this situation is the graph of the x cubed function. X cubed has a derivative 2x squared, so this function has the property that the derivative at 0 is 0, but the function value f of 0 being 0 is not in any sense a local extremum, because you see bigger and smaller values nearby. It's not necessarily true that just because the derivative is 0, the function has a local extreme value there. So, in order to capture this a bit better, we introduce the notion of critical points. We say that a point C on the x-axis is a critical point of our function f if the derivative at C does not exist, or if the derivative at C is 0. That's a new notion of a critical point, or critical point of the function f of x. Let's try this notion out in an example. Let's try and find the critical points of the function defined as x to the power 3 over 5 times 4 minus x. So, in order to list the critical points, we must find the points where the derivative doesn't exist and the points where it does exist but is 0. So let's compute the derivative first. That's the standard calculation by now. Power rule and product rule give the sum of mixed terms as the derivative of this product, which can be simplified to 12 minus 8x over 5 times x to the 2 over 5. This expression is 0 whenever the numerator 12 minus 8x is 0, that is, if x is 3 over 2. That's x equal to 3 over 2 is the only point where this derivative is 0. But then, looking at the denominator, which is a power, or 5 times the power of x, this denominator makes the derivative not defined for x equal to 0. Now we must not divide by 0, so this expression is not defined at x equals 0. So we found the critical points, one where the derivative doesn't exist, one where the derivative is 0. The critical points of this function f are 3 over 2 and 0. The use of critical points is that Fermat's theorem can now be reformulated in a more manageable way. And it can now be formulated as if f has a local extremum at C, then C is a critical point of the function f. That's a formulation which is no longer so heavy on the logic. If f has a local extremum, then C is a critical point. Still, one has to be careful to not read this backwards. The existence of a critical point doesn't guarantee the existence of a local extremum, but it suggests that we should look at critical points first when we are looking for local extreme values. So that's the basic idea of a strategy that allows us to locate global minima and maxima. And the idea is such an extreme value is either a local extremum or it occurs at the end point of the interval. So now here's the closed interval method, a 3-step procedure which allows us to identify the global extreme points of a function defined over a closed interval. So we assume that the function is continuous and defined over a closed interval from a to b. Then, in order to find the absolute maxima, the absolute maximum, there's only one, and the absolute minimum of a continuous function, that we go through these three steps. First, we identify the critical points of the function in the open interval from a to b, and for each critical point we calculate the function value f at c. Step 2, we calculate the function values of f at the end points a and b of the interval. And step number 3, we compare the values that we have, and the largest of them will be the absolute maximum, and the smallest of these values will be the absolute minimum of f on this closed interval. Well, here's a small example, a quadratic function f of x being half of x squared minus 2x plus 1, defined over the closed interval from -2 to 4. Of course, this function is continuous, being a polynomial. It's a continuous function. So the procedure, 1, 2, 3. Step 1, we find the derivative, which is x minus 2. This derivative is 0 exactly when x is 2, so c equal to 2 is the only critical point, and the value of f at c is -1. The values at the endpoints are straightforward. F at -2 turns out to be 7, f at 4 turns out to be 1. So we have computed 3 function values, which all are in competition for the largest and the smallest value. Comparing them, of course, 7 is the largest of them. That's the global maximum at -2. And the function value at -2 is 7. And it's obvious from the diagram here that this is the maximal value. And the smallest of the 3 values we calculated was the -1 at the critical point 2. So this is the absolute minimum value of the function over this interval. Now we'll finish this off with an application to a real-world problem where, I don't know, where maybe equipment needs to be protected from extreme temperatures. So a chemist models the temperature of a reacting mixture in an experiment as a function of time, f of t being 10 plus 5t minus the natural logarithm of 1 plus 40t. The time measured in minutes, the temperature measured in degrees Celsius. Let's say the experiment runs for 1 minute, that is from t equal to 0 to t equal to 1. That's a closed interval on the t-axis, on the time axis. And in the interest of protecting our equipment, we want to find the maximum and the minimum temperature of the mixture during the experiment. How do we do this? Well, we apply the closed interval method that we just saw. Step 1 there asks us to find the critical points. For this, we need to find the derivative of the function first, which is 5 minus 40 over 1 plus 40t by an application of the chain rule. So this derivative is 0 exactly when 5 equals 40 over 1 plus 40t, and that's easily solved for t, and it turns out the critical point is 7 over 40, and substituting 7 over 40 in the formula that defines the function gives the value 8.796 approximately. And that's the value at the critical point. At the endpoints of the interval, we find f of 0 obviously is 10, and f of 1 is 15 minus the natural logarithm of 41, which the pocket calculator tells us is approximately 11.286. So again, we have three values competing for being the biggest and the smallest, and obviously the biggest value of the three, 8, 10 and 11, is the value at the end point 1. So the maximum temperature is reached at the end of the experiment, and it would be 11.286, and the minimum temperature is 8.796 at the critical point, 7 over 40, some time into the experiment, and that's the minimum temperature of the mixture. So this is the closed interval method, which can be applied to find absolute extreme values. Next, we're going to develop a sequence of tests that use the derivatives, the first and the second derivative of a function, to identify and find local minima and maxima.